All right, let's get right into one of the absolute foundational building blocks of computer science, the array. Whether you're already writing production code every day, or you're just curious about how computers actually manage data under the hood, the concepts we're tackling in this explainer are literally the backbone of the software running our modern world. So, let's dive in.
To really get why the array even exists, we gotta look at the exact problem it solves. Picture this. You're trying to track a whole school's grades, right? And you're using individual variables for every single student. You'd have to write out code for grade 1, grade 2, all the way up to grade 1000. I mean, it would be pure chaos. It would be completely unmanageable, totally prone to typos, and frankly, a nightmare to debug. And that right there brilliantly illustrates exactly why we need a structured, organized way to group related data together.
So, to demystify all of this, we're taking a step-by-step building blocks approach today. We'll start with introducing the array. Then, we'll look at how array memory actually works, the different types of arrays, basic operations, and finally, we'll wrap up with searching and sorting arrays.
Okay, part 1, introducing the array. At its absolute core, an array is really just a collection of indexed buckets sitting right next to each other in the computer's memory. You can kind of think of it like a row of mailboxes at an apartment building. They're all totally identical, they're lined up sequentially, and they're designed to hold items of a similar nature, stuff like integers, characters, or strings.
Now, when you look at how these buckets are organized, you'll see that the index acts as a unique key to label each element. But here's the kicker. It always starts at 0, not 1. So if the length of an array is 5, meaning it holds 5 distinct elements, that final index is actually going to be a 4. This zero-based indexing is just a massive staple in most programming languages, and honestly, it's fundamental to how arrays operate mathematically behind the scenes.
Moving on to section 2, let's talk about how array memory actually works.
Because these elements are stored in contiguous memory, meaning they're sitting right side by side, the array doesn't have to go hunting around the hard drive to find a specific bucket. It just uses a simple mathematical offset. Basically, a pointer tells the computer exactly where the very first bucket lives, and the index tells it exactly how many steps to skip ahead to find the exact piece of data you're asking for.
In this underlying math, it's exactly why arrays are so essential. They provide O of 1 random access lookup time, which is pretty much the ultimate gold standard for speed in computer science. O of 1 basically translates to instantaneous access, totally regardless of how massive your dataset might be. Literally, whether you want the very first student's grade or the 1000th, the computer retrieves it instantly. It just takes that starting memory address, adds the offset, and boom, it's there. This completely explains why array operations can be so incredibly fast and why they're often the go-to choice over more complex data structures when raw retrieval speed is your absolute #1 priority. All right, section 3. Let's look at the different types of arrays.
Now, choosing the right type of array is crucial. You've got fixed arrays, which offer incredibly predictable memory footprints because their size is locked in the moment your code compiles. But the catch is, if you allocate space for, say, 100 items and only use 5, well, you've just wasted a bunch of memory. Dynamic arrays, on the other hand, give you ultimate flexibility. They actually allocate and deallocate memory on the fly during execution, basically stretching and shrinking as your program runs so you never have to worry about hitting a wall. And the cool thing is, those basic zero-index rules we just talked about, they apply no matter how many dimensions you add to store complex data. A 1D array is just your simple everyday list. A 2D array is more like a spreadsheet with rows and columns, perfect for things like data matrices or board games like chess. And you can even have a 3D array, which is essentially an array of spreadsheets, forming a literal cube of data.
Okay, section 4. Let's break down the basic array operations.
These are basically your fundamental tools. Traversing is simply looping through the array to look at every single item. Updating is just changing the data inside a specific bucket. Now, it's definitely worth noting that inserting an element at the very end of an unsorted array is incredibly fast, right? Because we just drop it into the next empty bucket. We don't have to worry about shifting anything else around. But what happens if we need to pull an item out from the middle?
Well, that brings us to the deletion operation. You can't just leave a gaping, empty bucket sitting in the middle of a continuous array. That breaks the whole structure. Instead, you essentially overwrite that deleted bucket by grabbing the element immediately to its right and sliding it one step to the left. And you have to repeat that shift for every single remaining element down the line, and then finally reduce the overall recorded size of the array by 1. It's a bit of a process.
Finally, section 5. searching and sorting arrays.
So if your array is completely unsorted, a sequential traversal, also known as a linear search, is going to be your go-to method for tracking down a specific piece of data. Honestly, it is the most straightforward, no-nonsense search algorithm there is.
See, a linear search really doesn't care if your data is a complete mess. It just stubbornly checks every single bucket, starting right at index 0 and marching down the line until it finds exactly what you asked for, or until it hits the very end and tells you the data simply isn't there. It's totally foolproof, but obviously if you have a million items, it might take a second. And that naturally brings us to sorting. This step-by-step logic introduces the incredibly famous bubble sort algorithm. Imagine scanning through pairs of adjacent elements in your array. If the number on the left is bigger than the number on the right, you swap them. Then you move over one spot and do it again. You keep doing this all the way down the line. And by the end of that first pass, the absolute largest number has effectively bubbled all the way up to the very end of the array, just like an air bubble rising in a glass of water.
But here's the question. How does the computer actually know when it's done sorting? I mean, it'd be a massive waste of processing power to just keep checking a list that's already perfectly sorted, right? So we optimize the code. We tell the computer to keep track of whether any swaps happen during a pass. If a full pass finishes and absolutely 0 swaps were made, well, that means all the buckets are finally in perfect harmony. The list is sorted, and the algorithm can confidently shut down.
Throughout this explainer, we've seen just how elegant and powerful contiguous memory can be. You get those instant lookups, straightforward organization, and super reliable algorithms. But think about the major weaknesses we just uncovered. Having to shift thousands of elements just to delete one single item in the middle, or having to completely reallocate memory if a static array suddenly runs out of space. I want to leave you with that provocative thought. What advanced data structure might step in when the super reliable array finally reaches its practical limits? Ponder that and keep questioning how the digital world is built.